This is going to be a research engineering talk. So for those of you who fine-tune models, want to fine-tune models, look at fine-tune models through one of the many frameworks in place, and have or have not wondered at points what happens behind the scenes when you change parameters or set config files. Hopefully, some of it might be answered today. For those of you who just see the cool things that fine-tune models give you, hopefully I'll be able to show you a bit of the kind of hoops we jump through to give you those fine-tune models. Those of you who are active researchers and think about the actual training of these models, I'm hoping we'll be able to see a bit of questions raising in your mind about why some of these things work. What if we did some other things with fine-tuning models? And this is hopefully not an audience that I need to convince why we need fine-tuning to start with. We have wonderful base models in the recent past. And as Charles said, a lot of us here are GPU poor. We want to fine-tune our models. A lot of us have tried and hit the out-of-memory error. And that's where the question of how to optimize certain things and what that does in the background and what that might do to our task-specific performances comes in. OK. All right. So this is the RAM bottleneck that most of us have hit at some point. If you haven't, I'm quite jealous of you. I have. And the question is that when you have available to you something like a T4, an NVIDIA T4, or an RTX 4080, how do you work with a model which is at least 7 billion parameters at the moment? How does that work? So a very, very simplified version of what your VRAM blocks look like. Every block here is 1 gig of memory. And what you have available is 16 gigs of memory to work with, let's say, a 7 billion model. That's Falcon, that's Llama, that's Mistral these days, a whole bunch of LLMs. There are 3 major sources of these bottlenecks. You need to work with your model parameters. You need to save your gradients. And the killer component is the optimizer states. There are a few other smaller things. Your activation weights have to be stored. There are other parameters that come in when you add new components, as you will see. But those are smaller, insignificant, somewhat insignificant details compared to these. So these are the 3 things that you worry about. These are the things that make you go out of memory. And we're trying to see what new techniques might exist that let us handle these. So quick refresher for some of you who might not have seen this. Most of the modeling that you do works in a mixed precision environment. What that means is we work with 16 precision floats, 32 precision floats, 64 precision floats. And what this differs in is the orange part, which is the dynamic range, which determines what is the range of values your model can handle. What is the range of floating point values it can handle? And in the blue part, which is how precise it is going to be. So there's a trade-off between the precision and the dynamic range as you go from one or the other. If you have fancy hardware, NVIDIA has come up with newer kind of floating point precision data sets, like BF16 or TF32 even. And the green and the yellow bits, again, are the dynamic range and the precision here. And as you can see, the trade-off is between what are the range of values you can represent and how precise you're going to be. You do need to be precise because if you are not precise enough, you run into the famous problems of vanishing gradients, and your dynamic range obviously needs to be able to cover everything that you have in your domain. So this is actually a slide from the NVIDIA blog, where they try to compare the performance of the new kind of TensorFloat precision variable. So broadly, this is what the situation looks like when you start to fine-tune a 7 billion model parameter, for example. So by default, or at the start, you would work with a 32 precision FP data structure. What that does is it's basically 4 bytes of memory, and when you extend that to 7 billion parameters, that means you are needing right there. We haven't even talked about the gradient or the optimizer states yet. Just to store your model parameters, you require 28 gigs of memory, right? You're already out of 12 gig memories, right? So what if we used half the precision? If instead of FP32, you used FP16. What does that do to your model parameters? That right off the bat cuts it down into half and brings it to 14 gigs, right? You are at least beginning to get some hope of fitting your model into memory. Some of you should be thinking by now, okay, great, you've cut down precision. What does that do anything to the performance of my model? Yes and no. That's an empirical question which is very specific to your task. At this point, for the purposes of this talk, take my word for it, that the performance degradation that you see from moving to FP32 to FP16 it is task dependent, but it is completely within the realm of reason. And at this point, that it is an open research question of how it affects each task. And anecdotally, I can tell you that we've seen more and more fine-tuned models doing better on related downstream tasks as the precision goes down. And that turns out to be completely fine. So focusing on the memory only at this point. You're still not in a position to store any gradients, any optimizer states yet. Here comes the idea of quantization. If you have worked with any kind of declarative frameworks with fine-tuning models, you have probably noticed this configuration parameter called quantization, which decides how many quantized bits you have. What is that? What is that doing? Quantization as a general idea is basically trying to say that I'm not going to try to represent every single floating point value, but I'm going to create X bit size of bins for it. So what you see at the top there is the distribution of floating point values. Now, a very naive way of doing this would be, okay, I'm going to equally space every bin, and every value that lies in that bin will be given one particular value, and that saves me a whole bunch of bits to save that value. Naive idea sometimes might work, but as you can see at the top, your floating point values are not distributed equally. So if you do a naive split, a naive quantization, you will end up biasing your representation of numbers to things that are less and less likely to appear as a value. So this is broadly the idea of quantization. Why we bring this up is if you quantize the value to 8-bit values, this is what it does to your memory distribution. Now suddenly your model parameters have shrunk to 7 gigs. And now that frees up space for gradient space. In general, what happens in fine-tuning models, especially 7B, is this layout. This layout is useful to remember. Your gradients are around the same size as the model parameters. So if you have managed to shrink your model parameters to 7 gigs, that means you've also managed to shrink your gradient values that get stored during the forward process to 7 gigs. What does that leave us with? That leaves us with still about 56 gigs of shortfall. And like I said, the optimizer state is what is the killer of pretty much all your memory woes. Anyone recognize what this is? I'm pretty certain all of you have used it. This is the magical Adam optimizer. Works beautifully, but is horrendously memory inefficient. So don't need to worry about what's going on here. Thing to remember or thing to notice here is that there are two things that it needs to keep track of. The MT and the VT, that's the momentum. And if you're using a simple SGD variant, you will only be, SGD with momentum, you will only be required to store the momentum values. What this essentially means is the optimizer state needs to hold 3 copies of whatever your number of model parameters are. And that is where the optimizer state basically just explodes. So the details are not important, but the important thing to remember is that this is where your fine-tuning endeavors basically just crash. So MSR, Microsoft Research, came up with this technique called low-rank adaptation. For those of you who have a linear algebra background, kind of already know where we're going with this, but for the others, this is what a low-rank decomposition of a matrix means. Again, don't worry about the mathematical details. Intuitively, what that means in an application sense, the rank of a matrix gives you the information content of a matrix. So the lower the rank of the matrix, the less information it's holding on to. So when you decompose an m by n matrix to m by k and k by n, it forces that decomposition to focus on patterns in your matrix data. And the idea now is that you're working with a much smaller k, but when you go back to your original m into k by k into n matrix, you're back to your standard m by n matrix. But since your k is very, very small, a low rank, a low k, or low r, what you're actually ending up tuning is a much smaller fraction of parameters. So this is what it looks like. It basically compresses your tunable parameters. For example, if you had a 1024 by 1024 matrix there, where D is 1024, what you would do is basically get a very low rank, 8 rank matrix, and which now uses only 1024 into 8 into 2 parameters instead of the 1024 into 1024. So you keep the W frozen, you tune only A and B, and once you have those parameters, it gets added to W. This is what LoRa does. It's a simple idea, but saves tons of memory. It brings it down to 0.1 to 1% of tunable parameters. And this is what your memory optimization looks like now. Now, because you've added a hyperparameter there, now you have to decide what the right rank is, what kind of, which layers are you working with. It does add an extra bit of what we call LoRa params here, right? But that's still a very, very minuscule fraction of what it is saving you. So we are already doing reasonably well, much better than where we started. Hopefully, people are slightly convinced about that. What else can we do? We've gone from 32 to 16. We have quantized some of our values, so we're not doing precise values, we're doing bins. We have compressed some of our tunable parameters, so we're not even tuning all parameters, we don't need to. There are actually nice theoretical hypotheses about how your weights are intrinsically very, very low rank. Intuitively think about how you don't always, every time, need to tune 7 billion parameters. You're not every time needing to change or modify each of your layers, right? That's what it means by weights being intrinsically low rank. One additional point there, activations do have to be taken into account for, but it's, again, a very small portion of that. If we could go from 32 to 16, we can go from 16 to 8. So should we go from 8 to 4? So this is a paper that came out this year, QLoRa. So now, instead of a full fine-tuning, you are not even keeping your base model at 32 or 16 bits. I'm going to quantize my base model to 4 bits now. What does that look like? Remember that quantization thing that I showed you? When you do it for integers, a very naive version looks like this. So a 4-bit integer can represent 16 levels, right? If I did it in a uniform, naive way, for example, if my value was 0.203, I would store it as index 10, because it's closest to 0.2. And my error at the point of dequantization would just be 0.03, which turns out to be nothing, really. So this is how quantization works. And this is a very naive version. The actual paper does it in a much more systematic, statistically sound way. This is just an example to show you how the indexing works. So at that point, your peak memory is at 13.5, roughly. You've added 1 gig of LoRa, and I hope it's clear that these are all very back-of-envelope calculations. But at the peak of your QLoRa configuration, you are now training, fine-tuning a 7 billion parameter model within about, in less than about 14 gigs of memory, which is a massive gain. There's a lot more to do in that direction. This is the basic. These are the basic, most obvious things that have been tried. QLoRa, for example, does this thing called paged optimizers, which optimizes the CPU, GPU communication, etc. And I'd encourage you to look at some of these. And like I said at the start, for those of you who delve into this deeper, think about what if, what else is there that we can optimize without sacrificing performance. I would encourage you to go through these references, and if you have any questions, I'll be happy to answer them. And this is quite easy to run in a Colab notebook, actually. So at the very least, check out the LoRa paper and see how the quantization bit helps. And I'm happy to take questions.